In this presentation, we'll begin our study of the transient response of linear systems. Now, we've already looked at the steady state response, the response to a constant input through the idea of DC gain, and we've looked at the response to a sinusoidal input through the concept of frequency response. Now we're particularly interested in the transient response, what happens immediately after a signal is applied. We're interested in particularly what the output signal does in time. How large is it? How quickly does it reach a steady state value if the input reaches a steady state value? We've had many examples where we've looked at transient response. For example, the gantry crane problem. So let's see what we know about transient response. For a linear time invariant system, we know that if we have an input x of t, that the output in response to this input is given by the convolution integral. In the convolution integral, the role of the system is taken by the impulse response, here shown as g of t. Of course, this is the inverse Laplace transform of the transfer function. Unfortunately, the convolution integral does not really give us much idea about what's happening in time in a general sense. Sure, we can calculate the response if given a particular x of t, but we have a hard time characterizing the behavior of the system in the time domain. To simplify this problem so that we can learn something, what we're going to do is study special cases. And the special cases we'll study are lower order systems. So we're not dealing with an arbitrary g of s. We'll deal with very simple transfer functions. And the second simplification we'll make, the second kind of special case, is to look at very particular kinds of inputs, special inputs, and the ones we'll be concerned with are the step and the ramp, and the impulse. In this presentation, we'll examine first-order systems, and in the following presentation, we'll look at second-order systems. So first-order systems. In this case, we're talking about a transfer function, g of s, which can be written as b naught over s plus a naught, or, if we switch to a time constant form, can be written as k over capital T s plus 1, where capital T is called the time constant, and k is the DC gain. Now the relationship here between the DC gain k and time constant and the original coefficients b naught and a naught is k equals b naught over a naught, and capital T, the time constant, is 1 over a naught. Let's note the following facts about the first-order system we're dealing with. First, the system has a pole at -1 over capital T. And for stability, capital T must be greater than 0. So the pole is on the real axis in the left half plane at -1 over capital T. For larger values of capital T, the time constant, -1 over t is closer to the origin in the complex plane, so farther toward the right. And if capital T is small values of the time constant, then -1 over capital T is to the left. Let's now look at 3 examples of first-order systems, and you'll find other examples in your textbooks, especially the book by Palm. The first example is a coil of wire, an inductive coil of wire. This may be modeled as a resistance and inductance in series. Then the relationship between the voltage applied to the terminals, which is the input, and the current flowing through the wire, which is the output, is I of s is equal to 1 over Ls plus R V of s. If we compare this to our time constant form, we'll find that DC gain k is equal to 1 over R, and the time constant is equal to L over R. Our second example is a linearized liquid level system. So here what we're dealing with is a change in the flow rate there's an average flow rate, capital Q bar, and then there's a difference from that average flow rate, small q. Small q can be either positive or negative, indicating either an increase or a decrease from the average value of the flow rate. The relationship between this perturbation to the flow rate, small q, and the perturbation to the height of the liquid, small h, is given by the transfer function, capital H of s equals r over RCS plus 1 times Q of s, where capital H of s is the Laplace transform of small h, capital Q of s is the Laplace transform of signal small q. C is the capacitance of the tank, and R is the resistance of the outlet. If you're interested, you can find more about this liquid level system in the textbook by Palm. Our third example is a mechanical system. We have a force acting on a mass. The mass may slide on a surface with viscous friction, and the viscous friction is given by a damping constant c. We're going to measure as the output the velocity of the mass. Our equation of motion is mv dot plus cv equals F, the input force. After we Laplace transform, we find the transfer function v of s equals 1 over ms plus c times f of s. Or, if we write it in time constant form, we have dc gain k equals 1 over c in the numerator, and in the denominator we have m over c as the time constant, capital T. So the important thing here is that many different kinds of systems that look very different from one another, all act as first-order systems. So we're interested in the general behavior of such systems in response to certain specific signals. So now we'll find the response of our generic first-order system, which is k over capital T s plus 1. We'll find its response to a unit impulse input signal. So x of t will be equal to delta of t, and x of s will be equal to 1. We can multiply x of s, which is equal to 1, times the transfer function, capital K over capital T s plus 1, and then we can inverse Laplace transform that to find y of t. And what we'll find is y of t equals capital K, the DC gain, over capital T, the time constant, times e to the minus t over capital T, u of t. This is the response of a first-order system written in terms of the DC gain and time constant to a unit impulse input signal. We've graphed it here, and you can see it starts off with a value of capital K over the time constant capital T at time 0, and then it decays, and the rate of decay is given by the time constant, since that decay is given by e to the minus t over capital T. We'll note that the area underneath this curve, shaded here, is equal to the DC gain, capital K. So we've seen that the response of a first-order system to a Dirac delta input is dependent upon the time constant, capital T, and the DC gain, K. Now let's look at the response of our first-order system to a unit step. So now x of t is a unit step, and x of s is 1 over s. We multiply that by the transfer function, k over capital T s plus 1, and that will give us the output y of s in the frequency domain. We'll take y of s and we'll partial fraction expand it into two terms, k over s and k over s plus 1 over capital T. We can then inverse Laplace transform this y of s, and we'll find two terms, one for the inverse Laplace transform of k over s, and the second for the inverse Laplace transform of k over s plus 1 over capital T. The first is k times u of t, and the second is k e to the minus t over capital T u of t. We can write those together in the form shown at the bottom of the page, and this is the generic response of a first-order system to a unit step. Y of t equals k times the quantity 1 minus e to the minus t over capital T times u of t. And there's a few things to note about this. First, the importance of the DC gain and time constant in dictating the response. And second, that as t goes to infinity, the output y of t will go to the DC gain k. Finally, note the rate at which the output goes to this final value. It's dictated by the rate of exponential decay in e to the minus t over capital T, and that is dictated by the time constant. So when the time constant is large, it will go to its final value slowly, and when the time constant is small, it will go to its final value quickly. So here is a graph of the response of a first-order system to a unit step input, and we'll note the following. First, if we draw a line that is tangent to the initial part of the transient response, and we draw it up to the final value that is achieved, which is the DC gain k, that this line will intersect the final value line, marked by the point labeled 1, at a value of time equal to the time constant. And that's shown here. Next, we'll note that the value of the output at a time equal to 4 times the time constant, capital T, is within 2% of the final value, k. It is within 2% at this time because e to the minus 4 is equal to 0.0188, which is approximately 2%. Referring back to the equation for the step response, you'll notice the exponential term will be e to the minus 4 when t is equal to 4 times capital T. Therefore, the value of y of t at this time will be within 2% of the final value. Now let's take a look at the response of the first-order system to a unit ramp input. In this case, x of t is equal to t times u of t, and of course, x of s is 1 over s squared. If we multiply this x of s times our first-order transfer function to find y of s, and then inverse Laplace transform, we'll find the following response. Y of t is equal to k times the quantity t minus capital T plus capital T e to the minus t over capital T u of t. Again, you'll note that the response is completely characterized by the DC gain and by the time constant, capital T. Now let's look at a graph of this time response. Shown in red is the response of the first-order system to the unit ramp impulse. I've also drawn 2 other curves here. In the darker blue, y tilde is equal to k times t, and this would be the response of a system that was just a gain k to the unit ramp. I've also shown another line in green, and this is y double tilde. It's equal to k times t minus capital T. You'll note the response of the system asymptotes to this curve. You should be wondering how quickly y of t converges to y double tilde. Well, the answer is given by the time constant again. We're looking for when e to the minus t over capital T becomes small. So as before, we know this will occur at approximately 4 times the time constant. Note that the difference between the two dashed lines is equal to k times capital T. So if the time constant capital T is small, the response y of t will be very close to y tilde. That is, the system will act as if it's just a gain, k, and not a first-order system, in response to the ramp input. Let's now look at the relationship amongst the various responses we found for the first-order system. We looked at 3 different kinds of inputs: the ramp, the step, and the impulse. And we'll note that these 3 different kinds of inputs are related one to another. The derivative of the ramp is the step, and the derivative of the step is the impulse. The same relationship holds amongst their responses. The derivative of the response to a ramp is the response to a step, and the derivative of the response to the step is the response to an impulse. So we can say the response to the derivative of x of t is the derivative of the response to x of t. This result is not just true for first-order systems, it's true for all linear time invariant systems. The reason why is that the linear time invariant system and the derivative are both linear operators, and linear operators always commute, so that we can switch the order, as shown in the diagram here. We can take the signal x, then take its derivative, then pass it through the system h, and get an output y. Or, if we take x and first pass it through h, and then take the derivative of that signal, we'll get the same signal in the end. The order does not matter. So we've now examined the response of first-order systems to a variety of typical inputs: ramp, step, and impulse. And we found in all cases that the response is characterized by the DC gain of the system k and the time constant capital T. In our next presentation, we'll examine second-order systems, and we'll learn what aspects of the transfer function act in the same manner as time constant and DC gain do for first-order systems.